Hello, everyone. In this lecture, we will learn the two sample versus the independent sample. And then later on, we will talk about the paired, how to make inference about the paired sample means. So what do we mean when we say paired and independent samples? Uh, Before, in the previous lectures, we've learned how to compare two population means, and we've seen how to construct a confidence interval between the difference between two population means, as well as how to perform a hypothesis test about the difference of two population means. But in that case, well, apologies, we haven't seen this one. It will be in the coming lecture, I guess. But we have seen how to construct and how to perform hypothesis about the difference of population proportions. So the notation is like this one. We have population notations or parameters, and we have for the sample mean notation and sample standard deviation notation. And now, when we say two samples are independent, this is when the selection of individuals who make up one sample does not influence the selection of individuals in the other sample. When we have this case, and a simple example of this one is when you select a sample from two different populations, we call the two samples independent samples. If they are totally from two different populations, in this case, we can say they are independent, and we don't care whether N1 and N2, I mean the sample size from population 1 and population 2, they don't have to be equal. We don't care about that one. Okay, it can be equally or they can be different. But the other case is when observations from first sample can be matched up in some meaningful way with observations in the second sample, then we said the two samples are paired. So in this case, N1 and N2 they have to be exactly the same. They have to be equal. Otherwise, they cannot match. Okay, but that's not the only way to see if samples are paired or not. One thing is sometimes, for example, if you want to make inference about, or if you want to study the effectiveness of, let's say, a new way of teaching, for example, what you could do is, for example, you could take one group of sample. You could select a group of students, and then you could give them a test prior to the new way of teaching, and have their record, and then introduce them to the new way of teaching, and then you give them another test, test 2 and test 1. Now, the thing is, we have the same group in both tests. And if you wanted to see the difference between these two tests, which means prior and post the introduction of the new way of teaching, then you could use a pair test, because these are not independent. They are the same group that we are using in both tests. Therefore, this is one example of pair test. Another thing is they can be different group. They can be different people in two different groups. Okay. But here you may want to, well, let's say, for example, if you may want to change a bit about this experiment. An example would be, for example, reading about this text, for example, if you make visualization on this text, so one text would be the same text. For one of them, you visualize some of the words, and for the other one, you don't. And then you give one to this group and the other one to this group, and let them scan it or see if it's relevant or not before they fully read it. And you measure how many seconds they may take to figure out whether that article is relevant to them or not. So this would be a simple, another example of paired samples. So once you have figured out whether your samples are independent or dependent, then the next would be making inference about based on a paired sample or based on independent samples. So first we will look at the paired samples, how to construct confidence interval about paired sample and based on paired sample, and how to perform hypothesis test based on paired sample. And the notation that we use here is mu sub d, which means mean of the difference population, and sigma d, standard deviation of the difference population. And of course, we will have x bar sub d, s sub d, and these are from the sample, mean of the differences and standard deviation of the differences. So in order to make a hypothesis or perform a hypothesis, we introduce the so-called paired t-test. This one, the idea is exactly the same with one sample t-test. One sample t-test. But before we go to the one sample t-test, let's see why we call it paired t-test. All right. Now, to compare two population means, when the samples are paired, we of course translate the problem into a hypothesis test. And basically the hypothesis will be using mu d, here we have, and we can have h sub naught equals to mu, said that mu d equals to hypothesized value. And this is equivalent with this one. We're saying mu1 minus mu2 equals to hypothesized value. Okay. And mu1 minus mu2 greater than hypothesized value is equivalent to mu d greater than hypothesized value, and so on and so forth. So this is the hypothesis. And when they are paired, the equivalent hypothesis becomes, or we write it this way. Okay. So in this section, or in this lecture, this is what we are learning now because it's paired. Okay. Now, for every inference, whether it's hypothesis test or confidence interval, we have conditions that we need to check before performing or doing the calculation or before reaching the conclusion. And for this paired sample t-test, the conditions are the samples are paired. Of course, in order to use paired sample, you have to check whether the two samples, whether we can regard them as paired or not. Otherwise, I mean, if we don't figure out this condition, then we don't know if we have to use paired t-test or independent sample t-test. Therefore, this is the first condition. And the second is the n sample difference can be viewed as a random sample from a population of difference. So what we mean by this n difference is, let's say we have x and y. We have data here, and we are saying these two are paired, these two groups, group X and group Y are paired. So what we do here is we find the column Y minus X or X minus Y, doesn't matter. We will, I mean, based on your hypothesis, and then you find the difference here. So this is what we are looking now, this difference. Now we ignore this. Once you have the difference, you ignore this one. So this column, that's what we mean the n sample difference, which means this column, is viewed as a random sample, or can be viewed as a random sample from a population of difference. Now, what we're saying is, can we regard this one as a random sample? Or can we say this is a representative of the differences, or the population, the population of differences? So that's what we mean. So we don't look at the X group or the Y group. We look at the difference group. Okay, can that difference group be a representative sample or a random sample? And then, well, we have the large sample assumption or condition, and the sample size has to be greater or equal to 30 in order to say it's a large sample. So once these conditions are met, then the test statistic that we use is given by t equals to x bar sub d minus mu sub d over s sub d over the square root of n. And if you remember, this is exactly the same with the one sample t-test, except this sub indices. We didn't have this indices d and d and d and so on. So, and this d is just to indicate that these are mean of the difference column. X bar is mean of this column. Mu d is the hypothesized difference. So S sub d is standard deviation of this column. And n, we don't add up these two n's. We have n because they are equal. N1 and N2 are equal because it's matched, they are paired. So it's always equal in this case. So we don't add this. When we say here n greater than 30, we look at one of them. So basically we look at the difference here. What is n here? Because this n is the same with this n's, of course, because it's the difference. So we just look at this difference, the size of these differences. And that has to be greater than or equal to 30 in order to assume it's a large sample. Or we have another one. We can see if it's approximately normal or not. And that's another case in order to satisfy that condition. Okay. Now the paired sample t-test, once all those conditions are met, here we have the null hypothesis written in this way. Mu sub naught equals to, such that mu sub d equals to hypothesized value. This hypothesized value could be 0, it could be negative, it could be positive. And then when the conditions above the three conditions are met, and this null hypothesis is true, the t-test that we have this t-test follows a normal t-test, a t-distribution, sorry, with n-1 degrees of freedom, just like the one sample t-test, exactly the same. And then, of course, we depend on the alternative hypothesis in order to find the p-values. So for each alternative hypothesis, we have different areas, or the areas are in different directions. All right, so let's look at this theory using this example. Okay, so suppose we have this okay, this is about visualizing web documents as tag clouds to aid users in relevance decision. So when you wanted to read an article or some article on the web, what we do is normally you don't go and start reading straight up. What we do is you kind of do a relevance, or you kind of scan it. You quickly look at it and whether you check whether it's relevant with your interest or not. So the researchers, they were interested in seeing or checking whether making some visualization to the document changes the users or the readers' interest or not. relevance decisions or not. So what they did was they chose 10 documents from the web, and they created a word cloud representation for each of them. Word cloud representation here is kind of, they made visualization. So that means they have one for each of the 10 documents. They made this word cloud, and they have the text as it was, like the document as it was. So for each document, they have two versions, that means. And then what they did was they gave those articles to different group of people. And then they were interested in the average time in seconds it took the people in the group to make a relevance decision based on those visualization and well, for the raw text and for the visualized text. So here we have the data. There are 10 people, and here is the time in seconds to relevance decision for the text version, and this is for the word cloud version. Okay, so this is how long it took for the people to decide whether it's relevant to them or not, and this is for the text version. And then the difference, text minus word cloud, we have it here. And going back, what is the question? Yeah, so they were interested in determining if a document was relevant if they first saw a word cloud representation of the document. So they were interesting. They were trying to see if it took them less minutes to decide or not. So coming to the calculation or to the procedure, here we have the sample values, and then, well, going step by step, the next is we need to figure out, or we need to set our hypothesis. So since this is a paired t-test, or it's a paired sample, we have mu sub d, which is mean difference in time. This is text minus word cloud. And we wanted to see if mu d equals to 0, and mu d, the alternate hypothesis is mu d greater than 0. And so in this case, if it is positive, it means it takes them longer for the text version to decide to make relevance decision. And then the method is, since we said they are paired, here is the test statistic given by this. And the reason we change this one is because the hypothesized value here is 0. So we change this hypothesized value to, or mu sub d to 0, because it says 0 here. Okay, so this 0 is from the null hypothesis. Now, when the null hypothesis is true and all the three conditions are met, then this will have a t-distribution with n minus 1, which is 10 minus 1 degrees of freedom, which is 9. And let's take the alpha 0.05. Then we need to check the conditions. So although the 10 documents are not a random sample, the researchers chose the documents to be representative. So if they are representative, then it's good to assume this is a representative sample. And the sample size is small, so we need to check the normality. We need to see whether this is normally, approximately normal or not, or if it violates the normality assumption. So in order this approximately normal normality condition, in order to violate this one, either the data or the graph has to be very skewed, or we need to see some outliers. So let's see. We have a box plot here. So here, yeah, it's skewed. It's skewed to the right. But the thing is, of course, this is a sample out of the whole population. This is a small sample. So this difference could be a sample thing. So as long as, and another thing, if you look at the box, it's not too far to 1 in. If you look at this median, it's not too far. Okay. So it's not super skewed here. If it was, for example, let's say this was here, the line, the central line, the median, or if it was somewhere in here, yes, it would have been skewed. But in this case, this being long on the right side, of course, it tells us it's kind of skewed, but not too much. Therefore, we can still assume it's approximately normal because this is more or less at this center. Therefore, I can use the paired sample t-test. Okay. Now we go to the calculations because we follow the steps. First, we set our hypothesis, and then we check the conditions. And now we have to make or we have to do the calculations. So n is 10 and x bar d sub d is this, and we have the standard deviation. So we find the t equals to the mean, this one minus 0 over the standard error of the differences, and then we have this. So since the alternative hypothesis is mu sub d is greater than 0, because of this greater, then the area would be, area of p-value would be to the right of the calculated value, which is this value. Okay. Therefore, we can either use the table, or we can use the salt. We have it here. So here 2.79 what was it, 4. As you can see, it's 0.01046. And of course, you can even use this step. All right, so since the p-value is approximately 0.01, we reject the null hypothesis because this is smaller than alpha. And here we have, because p-value is less than alpha, you reject h0, and we say this is convincing, or there is convincing evidence that the mean time to make a relevant decision for text documents is greater than the mean time for word cloud representations. So this is our conclusion. Now this is using based on the hypothesis test. How about confidence interval? How do we construct confidence interval for a paired sample? Okay, so the conditions are the same. There's no difference. And once the conditions are met, this is how we calculate or find the confidence interval with a certain confidence level. And the interpretation is the same with what we've been learning so far. Now, if we look at the same example, this is the same example, and here we have the difference column. And of course, we have already checked the conditions, so the conditions are the same. So, and we have checked them, so we will skip that step. And the method here is the paired sample t confidence interval. That's what we are going to use. So I will just straight jump to the calculation. So the t critical value for degrees of freedom 9 and a 95% confidence level, we are trying to construct a 95% confidence level for the mean difference. So the t critical value, how do we find this value? Well, let's go back to this one. And here we have degrees of freedom. I don't know this value. This is what we don't know. But we know this one, which means, okay, I will change this to between. So the between is 95% because that's our confidence level, okay? And that's between this value and this value. As you can see, they are the same in absolute value. Therefore, This is our critical value. And that's what we have here, 2.26, the positive value, of course. Now, substituting this value in the formula, this is the formula. We have x bar sub d, it's 0.489. We have the critical value, which is 2.26. And the S sub d is this one, and n is 10. So here we have the 95% confidence interval. And as you can see, both of them, they are positive. The lower limit and the upper limit, they are positive, which means we can assume the population mean, the population difference mean is greater than 0. All right, based on this samples, you can be 95% confident that the actual difference in mean time to make a relevance decision is somewhere between these two values. This is in seconds. It's time in seconds. So since both the endpoints or the limits are positive, we would estimate the mean time to make a relevant decision is greater for text documents than for word cloud representation, for somewhere between these two values. So what I mean by this is, when both of them are positive, then we can say that the mean difference is greater than, okay, let me write it here, because of course this is confidence interval, but for the confidence interval, for the hypothesis test, we had mu sub d greater than 0. So even without performing a hypothesis test, just by looking at this confidence interval, we know that we would reject this null hypothesis, even if we didn't perform this. Of course, for now, we have already rejected the null hypothesis, right? Because we did the hypothesis first. But suppose we didn't do that one, we didn't perform a hypothesis. Just based on this one, since both of them are positive, we would reject the null hypothesis, which says mu sub d equals to 0, because both of them are greater than 0. So we would reject the null hypothesis, and we would say for the text version, text longer than for the other visualized version. Okay. So this is the concept behind like the relation between a hypothesis test and a confidence interval. Had it been, for example, something like, let's say negative 0.094, if it was negative to 0. I'll just keep the same value. Suppose it was like this one, and one is negative, the other is positive, which means the 0 value is in between. Number 0 is in between. That interval includes the 0. In this case, we wouldn't reject the null hypothesis, because our null hypothesis says the mean is 0, and 0 is still in the interval. The 0 value is still in the interval. Therefore, we would fail to reject the null hypothesis in this case. But here, if it doesn't include the null hypothesis, the 0 value, the 0 number, then we would reject the null hypothesis. Okay. All right. So this is all for today, and see you in the next lecture.